This is the official podcast of Global Eco Trading. We manage global trading operations and provide access to exclusive international brands and specialty products. Our experience and expertise help clients secure high-quality goods and significantly reduce their operational costs. We supply not just merchandise, but trust and lasting value. Welcome back to the Deep Dive. Our goal, as always, is to take a complex stack of sources, articles, research, internal notes, and really just pull out the essential, actionable knowledge for you. And today, we're focusing on components that are, well, absolutely foundational to modern industry, but they're often completely invisible, high-precision industrial bearings.
It's so true. It's easy to just dismiss a bearing as, a simple round metal thing.
Right.
But these components they're true high-wire acts of engineering. They really show their strength in places that demand the absolute maximum precision and reliability.
We're talking about things like high-speed machine tool spindles, right? Aerospace?
Exactly. Aerospace guidance systems, advanced medical technology, they're everywhere.
It's a fantastic topic because the sources show this intense continuous evolution. So our mission for this deep dive is to trace that journey.
Yeah, how they went from these simple mechanical parts that were all about raw speed
To becoming these complex, digitized, and sort of integrated smart enablers of modern production.
It's an evolution that's really driven by manufacturers who are constantly chasing that next millimeter of precision or the next 1,000 RPMs of speed or another decade of service life.
Okay, let's unpack this.
Joey.
And I think we have to start in the past. Back when the name of the game was pure performance, sheer speed, the 80s and 90s. Looking at that era, the sources are pretty clear that the main design focus was simple.
Oh, absolutely.
It was all about achieving higher and higher rotational speeds to, increase throughput and meet those growing industrial demands.
That's exactly right. And the core technological breakthrough that really made this happen was the large-scale introduction of what we call hybrid bearings.
Hybrid, okay.
Which really just meant switching the rolling elements, so the balls inside the bearing, from traditional steel to ceramic.
That sounds like a fundamental swap.
Mm-hmm.
But it makes me wonder, if ceramic is so much better for speed, why were we even using steel for so long? I mean, are there huge cost penalties or maybe shock resistance issues that stop us from just switching everything to ceramic?
That is a crucial question. It's all about trade-offs. The ceramic they use, silicon nitride balls, is much more expensive and, frankly, harder to manufacture perfectly than steel.
So for those extreme speed applications, the cost is justified by the performance.
It is, and what's fascinating is how the physics pay off. Ceramic balls are, they're lighter and harder than steel.
Lighter means less mass, obviously. But what does that really mean in the real world when you're at, say, 50,000 RPM?
The consequence is a huge drop in heat generation, and, this is the most critical part, lower centrifugal forces. When a spindle is rotating that fast, those balls are trying to fly outwards with immense force. Reducing that force means the whole assembly creates less destructive heat, and it can run longer without a catastrophic failure.
So you're pushing the speed limit of the whole system way beyond what steel could ever handle.
Far beyond it.
So materials innovation gave us the speed. But the sources also talk about geometry being refined in that same era. It wasn't just what they were made of, but how they were shaped and installed.
Absolutely. Think of it as fine-tuning the physics inside the race. Engineers started using smaller balls within the same bearing diameter, for instance. But the real engineering feat was developing customized preload strategies.
Preload. Okay, that's a classic bit of engineering jargon. For anyone listening, is preload just how tight you screw the bearing on? Or is it something more specific, a kind of engineered internal tension?
It is absolutely the latter. Preload is a precisely calibrated internal force that's applied to the bearing when it's installed. It completely eliminates any play or slack, which is vital for rigidity.
And why is customizing that so critical?
Because machine tools don't just push down. They face forces from all directions, axial, radial, sometimes combined. If that preload isn't perfect, the tool head can deflect by just a few microns under load.
And you've ruined the surface finish on the part.
You've ruined the part, exactly.
Can you give us a quick example of the configurations they were using to get that directional stiffness?
Certainly, different arrangements became standard, like O, X, or tandem configurations. If you picture the bearings in pairs, an O arrangement has them facing outwards, which gives you superb stiffness along the axis.
Okay.
An X arrangement has them facing inwards, which is better at handling any misalignment. And a tandem setup is just for maximum load capacity in one direction.
So all these options meant the bearing could be perfectly tailored for whatever balance of speed and stiffness the machine builder needed. That focus on speed really dominated the early era. But once you hit peak speed, the market always asks, what's next? And what the sources show is that the answer around the 2000s wasn't more speed, it was longevity and affordability.
That's the shift. From the 2000s on, precision was still table stakes, of course, but the priorities changed. Service life, maintenance, and crucially, cost efficiency became really important. Manufacturers had to lower that total cost of ownership.
And how did that show up in the tech? What was the dominant trend that helped with maintenance and costs?
The big one was the widespread move to grease lubrication, which actively started replacing the old oil-air systems.
Right, the ones with all the pumps and plumbing.
Exactly. For the end user, this was a huge win. Grease meant easier handling, much lower infrastructure costs. You don't need all those pumps, filters, and regulators, and it had a much smaller environmental footprint, no more oil mist.
The cost argument is massive there. Those external systems were a major investment and a serious point of failure. But oil air was used for a reason, right? It was good at cooling. So what was the engineering challenge to make grease reliable enough for these high-heat components?
That was the hurdle. They had to match the cooling ability of oil air. And the innovation really came in the design of the sealed bearing itself. Manufacturers developed these incredible sealed bearings with integrated high-performance grease reservoirs.
So these weren't just standard seals.
Not at all. They were carefully engineered to hold on to the lubricant for the entire life of the bearing, but also to allow just enough heat to escape.
So you go from this expensive, high-maintenance external system to a sealed, self-contained unit that just runs for years.
Correct. It dramatically improves service life and cuts down on that expensive, unplanned downtime for maintenance. It was all about the grease chemistry and the seal technology delivering on that lower total cost of ownership. And when we pivot to today's world, the demands are, well, they're immensely complex. Modern machine tools are becoming incredibly compact, way more versatile, highly automated.
Which means the bearing has to deliver top performance in a tiny space and still be reliable for the long haul. Here's where it gets really interesting. Because with smaller, faster, more versatile machines, quality, especially that microscopic surface quality of the final part, becomes everything. So how are they tackling precision and life extension today?
The main technological lever now is the aggressive reduction of internal vibrations.
Vibration.
In modern ultra-high-speed grinding or milling, even the tiniest imbalance inside the component creates waves that show up on the finished surface.
Okay, so how do you reduce vibrations in something that is by definition spinning thousands of times a minute? We already have ceramic balls, so where's the new innovation?
It's in the bearing's internal architecture. Specifically, the cage designs, the little part that holds the rolling elements apart.
Right.
We're seeing a major shift to high-performance materials for those cages, specifically glass or carbon fiber reinforced PEEK.
PEEK, that's a high-performance plastic. So we're talking about using advanced polymers instead of the old metal cages.
Yeah.
That feels like a material innovation just as big as the switch to ceramics.
It is.
What's the specific advantage that reinforced PEEK gives you over, say, a brass cage?
It's a triple benefit, really. First, it's very resistant to lubricants and coolants. Second, it has a lower mass inertia than metal, so it contributes less resistance in heat.
Okay.
And third, maybe most importantly, the design allows for better lubricant flow inside the bearing. So you get even cool running. The result is higher stability, drastically less vibration, and a better surface finish on your part. But the most defining feature of today's bearing isn't just the mechanics, it's the digital integration. Digitalization isn't just improving the machine, it's baked into the design and selection process now.
So you're talking about the design phase, way before the bearing is even built. How does that digital side actually change the workflow for an engineer?
It allows for virtual prototyping. Advanced simulation tools and calculation software are now standard.
So instead of months of physical testing.
Exactly. Instead of that, an engineer can input the exact operating conditions. The loads, the speeds, the temperatures, and the software helps them quickly select the perfect bearing configuration. They can optimize stiffness, figure out the preload, and run countless what-if scenarios instantly.
That simulation power must save a huge amount of time and money. It means you can get a tailor-made solution without the years of physical R&D that it used to take.
It shortens development cycles dramatically, and it ensures the bearing is perfectly suited for the application from day one. It turns bearing selection from an art into a predictive science.
That ability to model and optimize digitally, That brings us perfectly into the future. Looking at the source material, it seems like there are four big themes shaping the next generation: sustainability, digitalization with AI, miniaturization, and electromobility.
And they are all completely interlinked. They reflect these huge global economic pressures. If we start with sustainability and energy efficiency, there's a massive push for components that use minimal energy and create minimal waste.
Which means just continuing that trend of low-maintenance, long-life components.
Precisely. It means more focus on self-lubricating systems and even better integrated grease reservoirs. The goal is a bearing that can run for the machine's entire lifespan with no external energy and no manual maintenance.
And if we're talking about maximum efficiency, we have to talk about gathering information, the digitalization piece. How far are we with getting real-time data from the bearing itself?
We're well past the experimental phase. Current smart bearing systems have integrated sensors that measure things like temperature, subtle changes in vibration, or even the condition of the lubricant.
Which is the foundation for predictive maintenance.
It is. It helps you anticipate failures instead of just reacting to them.
So we have the sensors, the nervous system, but the next step is connecting that data to a higher intelligence, right? The brain.
Absolutely. The next huge leap is integrating these smart bearings directly into broader IoT environments, feeding their data into, say, a central factory control platform. And this is where artificial intelligence becomes the crucial analysis layer.
How does AI change the game compared to just getting a standard maintenance alert?
AI can analyze this constant stream of data and spot complex patterns or anomalies that a human or a simple alarm would never catch. It allows for much more precise process optimization. The ultimate goal, as the research outlines, is true autonomy. Machines that can adjust their own operating parameters, maybe slow down the cutting speed just a tiny bit based on the real-time thermal load or vibration feedback from the bearing.
So the bearing becomes the key input for controlling the machine.
It becomes the decisive input. And moving beyond intelligence, another key driver is simply getting smaller. Miniaturization. It's being pushed by high-tech sectors like medical tech, think robotic surgery tools, and semiconductor manufacturing.
How small are we talking here?
We're talking about dimensions that are often just millimeters wide, getting close to the size of a grain of rice. And the performance challenge here is immense. Despite being tiny, they have to maintain absolute accuracy at incredible speeds, sometimes several 100,000 RPM. The physics are just brutal.
So you have to pack all the capability of a big industrial bearing into a micro component. How is that even possible?
The only way to do it is through developing new hybrid materials and ultralight ceramics, often paired with very specialized manufacturing techniques. It's the only way to get the necessary strength and stability in such a tiny package. And finally, we have to touch on electromobility and manufacturing. The EV revolution is a huge opportunity because high-precision, low-friction bearings are critical for improving the efficiency of electric motors.
And better efficiency in an EV motor translates directly to more range and better sustainability.
Yeah.
That's a huge market differentiator.
Precisely. And on the manufacturing side, we're seeing additive manufacturing, 3D printing, creating all new possibilities. Because 3D printing lets you create complex shapes without expensive tooling, you can get custom-designed bearing components.
Faster and cheaper than ever before.
Exactly. It offers incredible flexibility for very specific niche applications.
So what does this all mean? We've gone on this journey from the need for raw speed, swapping steel for ceramic, all the way to today's drive for sustainability and smart connectivity, using things like peak and AI. It's a remarkable story of how a classic machine element has just continuously reinvented itself.
The key takeaway for you, the listener, whether you're a distributor, manufacturer, or an end user, is that these high-precision bearings are no longer just passive components. They are now fundamental key enablers of intelligent production. Embracing these trends, sustainable lubrication, smart sensors, integrating that data with AI, that is absolutely essential for increasing productivity and securing a competitive edge.
That leads to a fascinating thought for you to mull over as you leave this deep dive. If the bearing is now the critical sensor, the primary physical source of real-time data that feeds the AI, are we moving towards a future where the mechanical component itself, its material limits, its built-in intelligence rather than the software, dictates the primary performance and innovation limits of the entire machine? Thank you for joining us. This was the Global Eco Trading Podcast. Subscribe so you don't miss upcoming episodes covering the latest business news. See you in the next episode.